In this episode of IMO series, we are going to look at this geometry question from the 10th IMO, hosted by the Soviet Union in 1968. We are required to prove that there is one and only one triangle whose sides are consecutive integers and whose one angle is twice as large as another. We can straight away draw a triangle and label the lengths as x, x plus 1 and x plus 2, where x is an integer. But before we go further, there is a handy tip to know. In a triangle, the longest side of the tree is always a side which is opposite the largest angle in the triangle, and the shortest side always faces the smallest angle. Using this fact, we can try out all possibilities. There are three cases, the first one of which angle CAB is twice the angle ABC. The second case is where angle CAB is twice the measure of angle BCA, while for the third and final case, we have angle BCA to be twice that of angle ABC. Let's focus on case 1. After labeling the sides and angles, we can use sine rule to obtain a few relationships between the lengths and angles in the triangle. Note that we use the fact that sine 180 minus 3a equals sine 3a. Next, we replace sine 2a and sine 3a using two famous identities, and doing so allows us to get the sine rule identity above in terms of only sine a and cosine a. We can then express cosine a in terms of x using one of the equations from the sine rule. Simplifying another equation allows us to express sine square a in terms of x as well. Now, we can get an equation in terms of x alone by using the famous identity which states that sine square plus cos square equals 1. Simplifying the equation and solving it, we see that x must be 4, as we reject negative 1 because length of triangle must be positive. We can substitute the value of x to find the angle A, which happens to be arc cos 3/4 in this case. It is worth noting that we are not yet done at this point. We have to substitute this x back into our sine rule equations to make sure that this x we have found indeed satisfy all the equations. After checking that this solution is indeed valid, by the converse of sine rule, we have proven the existence of a triangle which satisfies all the requirements of the question above. What we have not proven is that this is the only triangle which will work. To do this, we will show that none of the configurations in case 2 and case 3 would work. I will skip through most of the calculations we did earlier and present you with only the final quadratic equation, since it is completely the same as case 1. For case 2, it appears that our final quadratic equation is x squared minus x minus 3 equals 0, where there is no integer root for x, so case 2 doesn't work. Doing essentially the same thing to case 3, we see that the final quadratic equation is x squared equals 1. However, when x equals 1, the three side lengths of the triangle would be 1, 2, and 3. Such a triangle could not have existed, since it violates the triangle inequality, which says that the sum of lengths of any two sides of a non-degenerate triangle must be larger than the third side. Therefore, case 3 does not work as well, and we have solved the question as required. I guess this is a relatively straightforward and easy question. You definitely won't see this type of questions in the IMO competitions nowadays, but it is still fun to occasionally attempt easier questions from past IMOs as a confidence booster. We have come to the end of the video, and I look forward to seeing you in the next one.